In these couple examples, we're going to talk about when we have issues with finding derivatives. And we're going to look kind of at the visual first, that if something is differentiable, which basically means can you do the derivative of it, it implies that something is continuous, right? Remember, continuous is there's no break in it or anything like that. So if f is differentiable at any point, then f is continuous at that point as well. So it's continuous. So there's no break in it. So if you flip that, converse is if f is not continuous at a particular point, then f is not differentiable at that. So there's definitely a couple layers going on with this. For example, that for this, if f is not continuous, then it is not going to be differentiable, which means we're not going to be able to find a slope at this particular point, because is it this slope that we would be taking, or is it this slope that we would be taking? In order for this to work, you have to have this smooth transition. So let's say it's here, right? And so the limit exists, but you're also talking about the slopes have to have this smooth transition. So we got these slopes, maybe we'll go at the top. If this is our point, we got these slopes that are approaching the same slope, right? They're both kind of approaching this slope of 0 at the top. And so that's the type of thing that you're looking for. So we're going to be approaching the same slope on each side. And remember, it's because this whole idea is we're talking about a limit. So we're talking about these slopes having this nice transition into the exact same thing. We don't want this abrupt change, because the slope here and the slope here are not the same thing. We have this break. So if it's not differential, or if it's not continuous, then we're not going to be able to find the slope, right? Because you have two different potential slopes. Another issue is when we have a corner. So a corner is continuous, but that doesn't mean it's differentiable, because you have this slope here, this red one, which is drastically different than this slope, right? We have this abrupt change from one to the other. And so that's not going to be this nice smooth transition from one slope. Now at this point, we'd be perfect. The slope here and the slope here, we would be approaching that same slope on either side, right? So a corner is a problem. This one is a problem. This is what we call a cusp. Corners and cusps are problems. And the reason that this one's a problem is that the slope does not exist. That slope is actually something over 0. It's vertical. And so if you have a vertical, you have rise but no run. And so we have an undefined slope, which is going to be a problem. I know what the undefined slope looks like. I know that it's vertical, but doesn't mean that it's not differentiable. We have a problem with this part because, again, this slope and this slope kind of approaching different things. You have this positive and then you have a negative. Then you have this abrupt change from this negative slope to a positive slope, right? And then here's another version of that. This one looks a little bit better where it's a little bit smoother, but we still have this same problem we have a vertical slope. So again, I know what it is, but it's undefined. All right, so some things to kind of consider as you're going through it. So here's what we got. Let's summarize it a little bit. So if when is a function not differentiable at a point? If f of x is not continuous at x equals a, think vertical asymptote. Think a jump discontinuity. Think full. All right. So a vertical asymptote, a jump, a hole, we are not going to be continuous at that spot. If f of x has a corner at x equals a piecewise function could happen on that. Piecewise. So the graph is continuous, but it has this abrupt change from one direction to another at that point. An absolute value is a perfect example of that. Right, it has that V shape to it. Sure, there are others, but those are a couple good examples to kind of think of. So that's when a corner is going to happen. If f of x has a vertical tangent, right, at vertical tangent line at x equaling a. So think of when your slope is 1/0, aka undefined. Right, and so that example was a cube root of x or a square root of an absolute value where you have this square root look, and then because of the absolute value, you have it on the other side as well. Cube root's kind of the classic one that pops up from time to time, but those are the kinds of situations that you're looking for. So when do we have issues with derivatives? When we have breaks in graphs, because one slope, there are different slopes potentially on different sides, but it doesn't matter. We can't even get, we have to get through the continuous part first, which we don't have. If we have a corner, there's not a smooth transition from one slope to another. A cusp is also not a smooth transition, and we have some undefined. This one is a smooth transition, but at that point we have an undefined, so it's not differentiable at that point. All right, and those were a couple different examples of taking a look at how continuity and differentiability connect.